let's consider that we understand that work is change in energy. Okay, the way you figure work, okay, is integral f dot dx. Okay, so you look at that and we say, well, let's consider that you're moving from here to here at constant speed. So if you're going constant speed, then the change in kinetic energy is zero. Therefore, the work is going to be change in potential energy. So you move from one spot to another spot and change potential energy. Okay, so we got delta U. Now, we know that delta U is going to be the work done, so that's going to be the integral of f dot dx. Now to make it easy, let's assume we got a one-dimensional force. Okay, so I'll get back to the dot product later, but we have one-dimensional force, let's say, so let's say that delta U equals just integral f dx. Now, if you think about what is delta U is the difference in energy. So that's going to be delta U is going to be U final minus U initial. Well, what's that? Well, you get the same thing if you did the integral of du from initial to final. So that would also be U final minus U initial. So we could then say that the integral du equals the integral f dx. Well, integral of something equals integral of something else. That means that something equals the something else. So du has to equal f dx. So f equals du dx. Now, this is the force doing the work. So that means that there you had to have, if you're not changing, so in other words, if change in kinetic energy is zero, if you're not changing kinetic energy, that means that you're not accelerating. That means this work had to be pushing against some other force in order for the net force to be zero. So that other force had to have be already there. So that force was the force due to the potential. So that means that the force due to the potential is equal and opposite minus du dx. So that's the force from the potential. Now, what does that mean to us? Means if you were to have a graph of potential energy versus position, and potential energy versus position looks something like that. Okay, or let's make it a little more obvious. So something kind of like that. Okay, so the force due to the potential minus du dx. So that means if you put an object at this position x, it's going to have a force to the right because du dx, okay, du dx is negative right there. So that means that negative is positive. So the force to the right. If you were to put an object right here, then the slope is positive, but negative derivative would be a negative, so there's a force to the left. Okay, and if you put an object over here, then that's going to be a force to the right. Okay, if you put an object right here at the bottom, then the force is zero. If you put an object right here, the force is zero. So that would say that if you have a changing potential, then the force is going to be in the direction of the lowest potential. Things want to seek the lowest energy, the lowest potential energy. And so there's going to be a force pushing them to the lowest potential energy. Now, if you're here at the bottom of the trough here, if you get slightly out of position, there's a force that pushes you back. We would say that is a stable minimum right there. Okay. On the other hand, this maximum over here, if you get slightly out of position, then the slope keeps you going further and further away. So that's an unstable zero right there. So we have equilibrium. we have an equilibrium at two spots. One of them is a stable equilibrium, okay, and one is an unstable equilibrium. The stable equilibrium, if you push it out of position, it wants to go back where it came from. The unstable equilibrium, if you push it out of position, it tries to go farther out of position. There's several examples of this in terms of celestial mechanics. That you've got, for example, the Earth, you got the Moon out here. If you have an object and you put it 60 degrees in front of the moon or 60 degrees in the back of the moon, then if you push it out of position, then the combined forces of the Earth and the moon, the gravitational potentials, tries to make it go back, and so things at those spots want to stay in those spots. Whereas if you had some object like floating between the Earth and the moon, they're both pulling on it, but if it gets slightly out of position, it's going to go one way or the other. So that would be an unstable position right there. Okay, and so in celestial mechanics. Now, let's get back to this, what I had before, and that was that delta U integral f dot dx. Now remember, what is integral f dot dx? Okay, so again, this is the integral du. Okay, so f dot dx, well, it's not just dx, we're going to say that dx is really, dxi plus dyj plus dzk. So that means that this is going to be the integral of f sub x dxi, or f sub x dx plus f sub y dy plus f sub z dz. Okay, and so integral of that really is what that's telling you. And so that means that du, okay, it's going to be fx dx plus fy dy plus fz dz. Put a minus in front of the whole thing for the force due to the potential. Now, if there's no y or z components, then fx would be minus du dx. If there is no x involvement, then fy would be minus du dy. Okay, if there's no x and y involvement and it's only z, then fz would be minus du dz. Okay, now what this does for you is an interesting sort of thing. That means that you could then find the x, y, and z components. Okay, now in principle, if u was actually a function of x, y, and z, then we would have to rewrite that. We would say that the x component is minus the partial derivative of u respect to x. Partial derivative would mean you're pretending the y and the z is constant, and you just take a derivative with respect to x. The y component is minus the partial derivative of u respect to y. The z component is minus the partial of u respect to z. Okay, now in mathematics, we would write this sort of thing as a shorthand, and so we would say, oh wait, we can actually find all the different components here, because we would know that the force is going to be fxi plus fyj plus fzk. So we would say this is the minus the partial respect to xi minus the partial respect to yj minus the partial respect to zk. Well, this sort of thing that you do all the time, and so there's actually a name for it. It's called the gradient, and the symbol for a gradient is like an upside down delta. You put a minus in front. So that would be how you would actually write that. This is shorthand for doing that. Okay, take a derivative of the x in the x direction, derivative of the y in the y direction, and derivative of the z in the z direction. And so this is how you would actually write that relationship for forces. Now, I wanted to bring that out. We're not going to really do a whole lot with that this semester, but next semester we will use this a bit more heavily.